You know how we tend to think of things like a perfectly cut diamond as being forever, just unchangeable,
Hmm.
static.
Right. But even down at the molecular level, even in things we think are totally stable, there's this
Hmm.
constant, well, dance of transformation happening,
Yeah.
sometimes just incredibly slowly.
Uh-huh. And that actually brings us perfectly to what we're diving deep into today. Chemical
The
kinetics.
science of reaction rates.
Exactly. Chemical kinetics is all about understanding how chemical reactions actually proceed and, maybe most importantly, how quickly they happen. It's the study of the speed, the mechanisms of chemical change.
And we've got some really solid foundational chemistry materials to guide us through this exploration today.
Yeah, good stuff.
Our goal really is to pull out the essential ideas from these sources,
Yeah.
make them super clear, hopefully engaging and, immediately useful for anyone listening.
Yeah.
We want those aha moments without getting totally bogged down in like super technical jargon.
Absolutely. And it's not just abstract science, is it? Understanding kinetics helps us answer all sorts of everyday questions. Like, why does that apple on the counter turn brown?
Or how does a dentist's filling harden up and actually stay put?
Or even what's going on inside your car engine, turning fuel into movement.
It all comes down to the speed of chemical reactions. Fundamentally, a chemical reaction is just about substances changing their identities, their properties.
Right.
And when chemists look at a reaction, they're usually asking three core things. First, is this reaction even possible? Can it happen?
Feasibility.
That's thermodynamics. We look for something called DG, Gibbs free energy, being negative. That means it's spontaneous, it can happen on its own.
Okay. Question 2.
Second, if it can happen, how far will it actually go? Does it go all the way to products, or does it stop somewhere in the middle?
That sounds like equilibrium.
Exactly, equilibrium, the final balance point.
Yeah.
But our focus today is squarely on the third question. How fast does it happen?
The speed.
That's kinetics.
Okay, so let's get right into this idea of reaction rate. The sources we looked at use a pretty good analogy, comparing it to the speed of a car.
Yeah, it's intuitive how much change happens over a certain amount of time.
So in chemistry, the reaction rate is defined as the change in the amount, or specifically the concentration, of either a reactant or a product over a given time period.
Precisely. And you can look at it from two angles.
How so?
Well, you can measure how quickly the reactants are disappearing, right? Their concentration goes down.
Okay.
Or you can measure how quickly the products are appearing. Their concentration goes up. Either way, it tells you about the rate.
Let's make that a bit more concrete. Imagine a really simple reaction, say substance R turns into substance PRP.
Okay.
If at one time, let's call it TS, the concentration of R is R and P is P, and then later, at time T, they've changed to R and P.
Then the time elapsed, delta T, is just T minus T.
Simple enough.
And the change in reactant concentration, delta R, is R minus R. And for the product, delta P is P minus P.
Right. And from that, we get the average rate. Now, for the reactant R, the average rate is minus delta R over delta T.
Okay, why the minus sign? Good question. Think about it. R is being used up, so its concentration decreases. R will be less than R.
Ah, so delta R is actually a negative number.
Exactly. And we want the rate, the speed, to be a positive value. So we stick that minus sign in front to flip it. Makes sense.
Yeah, it does. And for the product P.
Much simpler. Its concentration is increasing, so delta P is already positive. The average rate is just delta P over delta T. No minus sign needed.
Got it. Now, what about units? Speed is miles per hour, meters per second. What about reaction rate?
Units are concentration per time. So typically, if we're measuring concentration in moles per liter, that's mole-ola, and time in seconds.
Then the rate is moles per liter per second, mole-olo.
You got it. And the material also notes, for reactions with gases, we often use pressure instead of concentration. So you might see rates in atmospheres per second at AMC. Pressure acts like concentration for gases in this context. Now, to really see this in action, example 3.1 in our source looks at the hydrolysis of butyl chloride. That's CH0Xe20 by 80 by 89 CO plus water gives CH0Xe20 by 8022 by 89 OH plus HCl.
And table 3.1 shows the concentration of the butyl chloride changing over time.
Right, and it calculates the average rate over different time intervals. And what's really interesting is the rate isn't constant.
It slows down?
It slowed down, yeah. As the reaction goes on, there's less butyl chloride left to react, so the rate naturally decreases.
Okay, so an average rate gives us a general picture, but maybe not the speed at one specific moment.
Precisely. For that, we need the instantaneous rate.
The rate right now.
Exactly. The rate at a very specific point in time. Mathematically, it's what happens when that time interval, delta t, gets incredibly small, basically approaches zero.
Calculus territory.
Yep. We use DRDT or DPT. The D
Yeah.
means an infinitesimally small change. So for the reactant, that's the DRDT, and for the product, DPDT, still need that minus sign for the reactant.
And the source shows how to find this on a graph.
It does. If you plot concentration versus time, the instantaneous rate at any moment is just the slope of line tangent to the curve at that exact point.
Like finding the slope of the hill right where you're standing.
Perfect analogy. Figures 3.1 and 3.2 illustrate this. For that butyl chloride example, they give specific instantaneous rates, like at 600 seconds, it's 5.12 times 10 to the minus 5 mol AU. Much more precise than an average over hundreds of seconds.
Okay. Now that R to P reaction was simple, 1-to-1. What about more complex reactions like, say, Hg plus Cl, arrow, HgCl? That's still 1-to-1-to-1.
Right. For every mercury atom that reacts, one chlorine molecule reacts and one mercury chloride molecule forms. So the rate of disappearance of Hg, the rate of disappearance of Cl, and the rate of appearance of HgClO are all the same.
But what about something like 2HiHEO2 plus IO? Two hydrogen iodide molecules break down to make one hydrogen and one iodine.
Now it gets interesting. Hi disappears twice as fast as H or IO appear, right?
Yeah, because you need two HIs for every one HO.
Exactly. So to get a single, unambiguous rate of reaction that describes the whole process, we need to account for these numbers in the balanced equation, the stoichiometric coefficients.
How do we do that?
We divide the rate of change for each substance by its coefficient. So for 2HI H plus I, the rate is defined as minus 1/2 times the change in HI concentration over time
Magnitude 12.
equals the change in H concentration over time.
Ah.
Okay.
Yeah.
Dividing by the coefficient normalizes everything. So we get one consistent rate value for the overall reaction.
You've got it. It ensures consistency. The source gives another more complex example. 5 bro plus bromine plus 6 HU plus 3 euros plus 3 HO.
Whoa, okay. Lots of coefficients there.
Yeah. So the rate would be minus 1/5 the rate of change of bro
Okay.
equals minus the rate of change of bro
Bro.
equals minus 1/6 the rate of change of arrow equals positive 1/3 the rate of change of bro equals positive 1/3 the rate of change of bro. Wow. Okay. It looks complicated, but the principle is simple. Divide by the number in front.
That's the key takeaway. And remember, for gases, you can do the same thing using changes in partial pressure instead of concentration.
Right. Okay, so that's what rate is and how we express it, even for complicated reactions. Now, what actually affects the rate? What makes a reaction fast or slow?
Good question. The sources highlight the main players, experimental conditions, things like reactant concentrations or pressures for gases,
Temperature.
definitely temperature, and whether or not you have a catalyst present.
Let's start with concentration. We already saw with the butyl chloride example that as its concentration dropped, the rate slowed down.
Yeah, that's a very common observation.
Yeah.
Generally, if you have more reactant molecules packed into the same space, higher concentration, they're going to bump into each other and react more often. So higher concentration usually means a faster rate.
Makes intuitive sense. More cars on the road, more chance of collisions.
Kinda, yeah. And this relationship between rate and concentration is captured mathematically in something called the rate law.
Also called the rate equation or rate expression.
Same thing. It's a formula that shows exactly how the reaction rate depends on the concentration of each reactant.
So for a general reaction, let's say A plus BB goes to products.
The rate law usually looks like this. Rate equal K times A raised to the power X times B raised to the power Y.
Okay, let's break that down. A and B are the concentrations of reactants, A and B.
Right. Molar concentrations usually.
And K is the rate constant. What's that?
K is super important. It's specific to a particular reaction at a given temperature. Think of it as reflecting the intrinsic speed of that reaction. A large K means a fast reaction. A small k means a slow one.
Okay. And X and Y. They look like the coefficients A and B from the balanced equation.
But here's the critical point.
Oh.
They're not necessarily the same as A and B. Absolutely. The exponents X and Y, which we call the orders of reaction with respect to A and B, must be determined experimentally. You can't just look at the balanced equation AA plus BB and say the rate law is Cambens. It might be, but often it isn't.
Wow. Okay. That's a huge point. You have to do experiments.
They have to do experiments. The rate law summarizes experimental observation. We sometimes write it as a differential rate equation too, dash dRdt, linking the instantaneous rate to concentrations.
How do they figure out X and Y experimentally?
The source uses a reaction 2NO plus O euro as an example, with data in Table 3.2. Basically, you run experiments where you change the starting concentration of one reactant while keeping the others constant, and see how the initial reaction rate changes.
Ah, so if you double the concentration of NO and the rate goes up by 4 times.
Then the rate depends on NO squared, so X would be 2.
And if you double the O Euros concentration and the rate just doubles.
Then the rate depends on O to the first power, so Y would be 1. For this specific reaction, 2NO plus O eros, 2NOO, it turns out the rate law is rate italino or euro. So here the exponents do match the coefficients.
But that's not always the case.
Definitely not.
Oh.
The source gives other examples. Chloroform reacting with chlorine, CHClin plus ClO plus HKLO. The experimental rate law is rate HKTHKLO a half power.
Whoa! And another one, ethyl acetate hydrolysis, Chase KKAC plus HKA plus CHAH. The rate law is rate KCHCO or H arrow.
Zero order with respect to water. That means under those conditions, changing the water concentration doesn't affect the rate at all. Maybe there's so much water it doesn't matter, or it's involved in a later, faster step.
Fascinating. So these exponents, X and Y, lead us to the concept of reaction order.
Precisely. The overall order of the reaction is just the sum of those exponents in the rate law. So for rate H of K, the overall order is X plus Y.
And you can also talk about the order with respect to a specific reactant, right? Like order X for A, order Y for B.
Exactly. And these orders, as we saw, can be whole numbers like 0, 1, 2, 3. But they can also be fractions.
Like that 12 we saw.
Or even negative, though that's less common.
Zero order is interesting. The rate is completely independent of that reactant's concentration. Rate aerobo, constant rate.
Yeah. Doesn't matter how much A you have, the reaction just chugs along at the same speed, usually limited by something else, like a catalyst being saturated.
Example 3.3 just shows how to add them up. Rate AOBOBO, the overall order is 12 plus 32, force 2. Second order overall.
Or rate A go B, overall order is 32 plus negast 1 equals 12, half order overall.
And that negative 1 means adding more B would actually slow the reaction down.
It implies that, yes, maybe B inhibits a crucial step or something complex is going on. It all comes from experimental data.
Okay, let's shift gears a bit and think about how reactions happen on a tiny molecular scale. The source talks about elementary versus complex reactions.
Right. An elementary reaction is one that happens in a single step. Just one collision or one molecule breaking apart, boom, it's done.
Like AB or A plus B.
Exactly. Complex reactions, though, are the sum of multiple elementary steps happening in sequence. There might be intermediates formed and consumed along the way. It's like a pathway with several steps.
Could be consecutive steps or reactions going backwards or even side reactions happening at the same time.
All of those are possible in complex mechanisms.
Now, for those single-step elementary reactions, there's a concept called molecularity.
Yes, and molecularity only applies to elementary steps. It's simply the number of reactant species, atoms, ions, molecules that collide and participate in that single step.
So if one molecule just falls apart, like ammonium nitrite decomposing.
That's unimolecular. Molecularity is 1.
If two things collide, like two HI molecules breaking down.
That's bimolecular. Molecularity of 2, very common.
And if three things collide at once, like 2NO plus O or...
Molecular. Molecularity of 3. These are much rarer.
Why rare?
Probability. Getting 3 specific molecules to all hit each other at the exact same instant with enough energy and the right orientation, it's just not very likely compared to two-body collisions.
So if you see a balanced overall equation that looks like it involves way more than 3 molecules.
Like that KClO plus 6-cis-HO plus 3HOs example, 10 reactant species.
Yeah, that cannot be an elementary reaction.
Absolutely not. It must happen through a sequence of simpler elementary steps, usually unimolecular or bimolecular steps.
And the overall speed of that whole sequence.
That's determined by the slowest step in the mechanism. We call it the rate determining step, or RDS.
Like a bottleneck on a production line.
Exactly like that. Or a relay race. The team is only as fast as its slowest runner. No matter how fast the other steps are, the whole reaction can't go faster than the RDS.
This source uses the decomposition of hydrogen peroxide catalyzed by iodide ions as an example. 2 HROs, 2 HRO plus RO.
Right. The mechanism involves 2 steps. First, HRO reacts with IO to make HO and IOO. That's the slow step, the RDS. Then that intermediate IOO reacts quickly with another HOO molecule to make HO-OOer and regenerate the IO catalyst.
Ah, so the IO gets used and then reformed, and the IO is just temporary?
Exactly. IOR is an intermediate. And because the first step is slow, the overall rate law matches that step. Rate equals KHOOO, which is what's observed experimentally.
So let's quickly summarize the difference between order and molecularity again.
Okay. Order Comes from experiments. Rate law exponents can be zero fraction, integer, applies to overall reaction or steps. Molecularity, theoretical concept only for elementary steps, must be a positive integer, usually 1 or 2, rarely 3. Counts molecules colliding that step.
And for complex reactions, the order often reflects the molecularity of the slowest step.
Often, yes. That's a key link between the mechanism and the observed kinetics.
Okay, great. Now, we talked about the rate law, that differential equation, but often in the lab or, in applications, we want to know concentration at a specific time or how long it takes to reach a certain concentration.
Right. We need to go from the rate of change to a direct relationship between concentration and time. That requires integrating the rate law.
Calculus again.
Yep, but the results are super useful. The source focuses on the integrated rate laws for zero-order and first-order reactions.
Let's take zero order first. Rate equal K, constant rate.
If you integrate that, rate equal drdt equal K, you get a pretty simple equation. R8 plus R arrow.
Okay, R is concentration at time t. R is the initial concentration at t. 0K is the rate constant.
And notice that's the equation of a straight line, y equal mx plus b. If you plot r versus t, you get a straight line with a negative slope equal to my k, and the y-intercept is the initial concentration r.
Figure 3.3 shows that plot. Where do we see zero-order reactions?
They're a bit uncommon but happen under specific conditions. Enzyme catalysis when the enzyme is totally saturated with substrate is a classic example. Adding more substrate doesn't help. The enzyme is working flat out.
Makes sense.
Also, reactions on solid surfaces, like decomposing ammonia gas on hot platinum. If the surface is fully covered, the rate depends on the surface area, not the gas concentration above it, so it can be zero order in ammonia.
Okay. Now, first-order reactions. Rate, Kr. Rate is directly proportional to how much reactant you have left.
Integrating this one, dash dr dt equals kr, gives us a logarithmic relationship. lnr equals lnr plus lnr. lnr is the natural logarithm.
So concentration decreases exponentially with time.
Exactly. The exponential form is r equals ree. And again, we can get a straight line plot. If you plot the natural log of the concentration, lnr, versus time, del nRt, you get a straight line. This time the slope is k, and the intercept is lnr arrow. Figure 3.4 shows this.
Are first-order reactions common?
Oh yeah, very common. All radioactive decay processes are first order. Many decompositions, like NOR or NRO, follow first-order kinetics. Hydrogenation of ethene is another example.
The source also gives the equation using base 10 logs.
All right, sometimes that's more convenient. KK equals 2.303 T log.
Yeah.
And you can plot log versus T to get a straight line with slope K 2.303, as shown in figure 3.5.
Example 3.5 works through calculating K for N-euro decomposition using this. And 3.6 shows how to adapt it for gas phase reactions using partial pressures.
Yep, the principles are the same, just substituting pressure for concentration where appropriate.
Another really useful idea related to these integrated laws is half-life. The half-life.
Super intuitive concept. It's just the time it takes for the concentration of a reactant to drop to exactly half of its starting value.
How do we calculate it?
Depends on the order. For a zero-order reaction, you plug R equal RE2 into the integrated rate law. R equals to TT plus R in solve, which becomes TT.
And the result is?
TT arrow is R2K. Notice something important here.
What's that?
The half-life depends on the initial concentration, R. If you start with more stuff in a zero-order reaction, it takes longer for half of it to react away.
Okay. What about first order?
For first order, you plug RNRE2 into LNR equals LNRAT plus LNRA. So LNR2, it's get arc equals down arrow plus LNRA. Rearranging gives LN2 equals KT arrows.
And LN2 is about 0.693.
Exactly. So T arrow 0.693K. Look at that equation.
The initial concentration R arrow isn't in there.
Bingo. For a first-order reaction, the half-life is constant. It doesn't matter if you start with a lot or a little.
Yeah.
It always takes the same amount of time for half of whatever you have at that moment to react. It only depends on the rate constant K.
That's a really key difference. Constant half-life for first order, concentration-dependent half-life for zero order.
You got it. Examples 3.7 and 3.8 show calculations, and 3.8 points out that for first order, after about 10 half-lives, you've consumed roughly 99.9% of the reactant.
And Table 3.4 conveniently summarizes the rate laws, integrated laws, plots, and half-lives for zero and first order. Very handy.
Definitely a good summary table.
Okay, let's shift focus again. Temperature. We kind of know intuitively that heating things up makes reactions go faster. Cooking, for instance.
Absolutely. It's one of the most significant factors affecting reaction rate. The source mentions N-euro decomposition speeds up with heat. The reaction between permanganate and oxalic acid goes faster when warm.
There's even a rule of thumb, right, that rates often double for every 10 degrees Celsius rise.
Yeah, a rough guideline. Not always exact, but it captures the strong dependence. So yes, cooking is applied chemical kinetics. You raise the temperature to speed up the reactions that transform raw food into something cooked. You're overcoming activation energy barriers faster.
Activation energy. That sounds important. The quantitative relationship between temperature and rate constant comes from the Arrhenius equation, right?
That's the one. K equals A times E raised to the power of minus E over RT.
Okay, let's unpack that. K is the rate constant. T is the absolute temperature in Kelvin. R is the gas constant. What are A and E?
E is the activation energy. It's the minimum amount of energy that colliding molecules need to actually react. Think of it as an energy barrier or a hump they have to get over.
Like pushing a ball uphill before it can roll down the other side?
Perfect analogy. Even if the overall reaction releases energy rolling downhill,
Mm.
you often need that initial input, that activation energy to get it started. Figure 3.7 shows this energy profile. Reactants activated complex, top of the hill, products.
In A.
A is the pre-exponential factor or frequency factor. It's related to how often molecules collide and whether they have the right orientation when they do collide. That's at the maximum possible rate if all collisions had enough energy.
So the A part tells us the fraction of collisions that actually have enough energy.
Precisely. That exponential term is always less than 1, and it gets bigger, closer to 1, as temperature T increases or as activation energy decreases.
How does temperature increase the fraction with enough energy?
That's explained by the Maxwell-Boltzmann distribution of molecular energies. Figures 3.8 and 3.9 show this. At any temperature, molecules have a range of energies. When you increase the temperature, the whole distribution shifts to higher energies and spreads out.
Ah, so the area under the curve representing molecules with energy greater than E gets much larger at higher T.
Exactly. A much larger fraction of molecules now possess the minimum energy needed to react, leading to more successful collisions per second, hence a faster rate.
Is there a way to use the Arrhenius equation experimentally,
Right.
plotting things?
Oh yes. If you take the natural logarithm of both sides, you get lnk e arrow 1t plus ln a.
That looks like y equal mx plus b again.
It is. If you plot lnk on the y-axis versus 1t, the reciprocal of absolute temperature,
Oh,
on the x-axis, you should get a straight line.
and the slope is EOR.
Correct. So from the slope, you can calculate the activation energy, E euro, and the y-intercept gives you ln a. So you can find the pre-exponential factor a. Figure 3 shows this plot.
Very clever. And there's a version for comparing rates at two different temperatures.
Yep. Log E euro 2.303R, 1t euro. If you know E and K euro at T, you can calculate K at a different temperature T. Examples 3.9 and 3.9 show how to crunch these numbers.
Okay, almost there. Last couple of factors. Catalysts. We hear about them a lot. Catalytic converters in cars, enzymes in our bodies.
Right. A catalyst is a substance that increases the rate of a reaction without itself being consumed in the overall process. It participates, but it gets regenerated.
And an inhibitor does the opposite, slows things down.
Correct.
So how do catalysts speed things up? Do they just lower the activation energy?
That's the primary mechanism. They provide an alternative reaction pathway, a different mechanism, that has a lower activation energy barrier. Figure 3.11 illustrates this beautifully. The catalyzed path has a smaller hump to get over.
So more molecules have enough energy to react via this new pathway.
Exactly. The catalyst might form temporary bonds with reactants, creating an intermediate complex that then breaks down more easily to form products and release the catalyst.
Importantly, catalysts don't change the overall energy difference between reactants and products, right? They don't affect the thermodynamics or the equilibrium position.
Crucial point. They don't change if a reaction can happen or how far it goes, equilibrium constant. They only change how fast it gets there. They speed up both the forward and reverse reactions equally, so equilibrium is reached faster, but the final balance is the same.
Got it. And finally, the source briefly mentions collision theory.
Yeah, a more theoretical look at rates. Based on kinetic theory of gases, molecules are treated like tiny hard spheres that have to collide to react.
So the rate depends on how often they collide. Collision frequency, z.
Partly. And also on the fraction of collisions that have enough energy, that ESI factor again. So initially rate Z,
But that's not the whole story.
not quite, especially for molecules that aren't simple spheres. Just hitting isn't enough. They also need to hit with the right orientation for bonds to break and form correctly.
Ah, like trying to fit two puzzle pieces together, they have to be aligned properly.
Good analogy. So collision theory introduces a steric factor, P, which is basically the probability that a collision has the right geometry. The improved equation is Rate, E is a PZEO?
And PZ is related to the Arrhenius factor, eh?
Roughly, yes. Collision theory gives a microscopic interpretation for the Arrhenius parameters. It has limitations. Molecules aren't hard spheres, internal structure matters, but it's a useful starting point for thinking about collisions, energy, and orientation.
Okay, wow. That was quite a journey through chemical kinetics. Let's try and quickly recap the main ideas.
We started with reaction rate, how fast concentrations change, average rate versus instantaneous rate, and how to handle stoichiometry using coefficients.
And the factors affecting rate. Concentration, leading to the rate law, rate, Kitzke-Fem, where the exponents x and y give the reaction order and must be found experimentally.
Right. We distinguish order, experimental, from molecularity, theoretical for elementary steps, and saw how complex reactions happen via mechanisms, often with a redetermining step.
Then we integrated the rate laws for zero and first order to relate concentration and time directly, leading to the concept of half-life constant for first order dependent on initial concentration for zero order.
We saw the huge impact of temperature, quantified by the Arrhenius equation, linking the rate constant K to activation energy E and temperature T.
And how catalysts speed things up by providing a lower energy pathway without affecting the overall thermodynamics or equilibrium.
And finally, a quick look at collision theory, emphasizing the need for sufficient energy and proper orientation for a collision to lead to reaction.
Understanding all this really gives us a powerful toolkit for predicting and even controlling how fast chemical changes happen, from industrial processes to, well, biology.
Absolutely. It sheds light on so many things we see around us, answering those questions you had right at the start about everyday phenomena.
And on that note, here's something to maybe mull over after listening. Think about all those countless, incredibly complex chemical reactions happening inside your own body right now, or in the environment. How on earth are the rates of all those different reactions being so precisely controlled and coordinated within those systems?
It's a staggeringly complex dance.
It really is a
Mhm.
truly dynamic world at the molecular level, and hopefully now everyone has a much deeper feel for the kinetics, the speed that drives all that change.